Yeah, this doesn't work. All right. So, first off, do people want me to talk about the Hawaiian lab a bit? Okay. So let me go ahead and put you on the right direction for solving that Hawaiian lab. Okay. So I'm going now. That said, I'm not going to explain that. What I'm going to do is I'm going to assume that you've already read through the assignment and tried, your hand at it. And if you haven't, well, then refer back to this lecture later. So there's a couple things we need to do with the Hawaiian lab. Okay. So first off, we need to define the functions that we're going to be using in the Hawaiian lab. And why functions? Because I want to break this down into small modular chunks that I can work on separately. Right? There's basically three things I need to do. Get the input, which really doesn't require a function. In fact, let's do that last. That should be the last step because honestly, input is fairly easy to do at this point for us. But there are two other tasks that are harder. The first is basically checking if it's a valid word or not. Given some text, I want to know if that is a valid Hawaiian word. Okay. I'm just going to put here and what I'm going to do with that is I'm going to assume that it is. I'm going to return true and assume that it is a valid Hawaiian word until I am proven otherwise. This allows me to decide, and the reason for this is that you can work on this part or the next part first. It doesn't matter which one you want to do, and you can test them separately. Okay. Right. So, and I'll put a description in a multi-line string right below it, which is checks if word is has only valid letters in it. Assumes word is string, returns true if valid, Hawaiian word, false otherwise. Sorry, if right, that's what we got here. And if you're frantically typing it down, don't frantically type it down because I'll probably make some iterations and I'll just post it on Discord. Okay. So that way there's no issues with like accidentally something. The second task that you're going to want to do for this one is the task of pronouncing the word. Or let's go with actually pronounce word. So and for this one, we're going to assume that what we're given is a valid Hawaiian word. Okay. So given a valid Hawaiian word, returns a string. I'll put that in a separate line. Returns a string that gives the correct enunciation. Okay, that's basically what that does. So for this one, what I'll say is that what I like to do is like say, okay, now the pronunciation, what we're going to do is we're going to essentially go phoneme by phoneme, right? In other words, sound by sound, and add that sound into an output, right? So we see, okay, that's a T, so we're going to, or sorry, that's an H, so that's going to be a H sound. And then we've got an AI taken together, that's going to be sound like an I. And then we add that to our output. So this is an accumulation pattern with a string. So I'll just simply say, we can call it pronunciation, we can call it output. I'm just going to call it output because that's something I commonly refer to my string as. And so, and then we'll return the output And obviously the actual work happens in between those two lines, right? Okay. But the idea here is that pronunciation is going to assume that validate works, but it doesn't depend on it for testing purposes. Okay. Similarly, validate is just going to check whether it's true or false. It doesn't care about how to actually pronounce it. It just says, does this word work given the rules that I've given you? Okay. Now for the so what we're going to do is, or at least what I'll do, is that I like to test these on these following words. K-key, K-I-K-I, which will, if you do it correctly, will be pronounced as K key. If you do it incorrectly, you will instead get, if you do it incorrectly, you're going to give me, then you'll be getting back K E key. Okay. The other word I like to check is humu, nuku, apu, you know, humu, nuku, apua. Did I spell it right? I think I did. Which is, of course, as everyone knows, the Hawaiian state fish. So, but that one just, so this one doesn't have any valid double vowels in it, right? UA isn't a valid double vowel pronunciation in Hawaiian. I don't think, but it should be humu, nuku, apu, apostrophe ah. So this will help test whether you've got apostrophes working as well as, yeah. See, yep, apostrophes count. Which really they just kind of sit, and the way that kind of works is that if you see an apostrophe, you just output an apostrophe. All right. Now, first, what we want to do is, now, how do we solve this? Because this is where we kind of get into the issues, I'm sure. Then the answer is that you can't use a standard for loop for this. I really want to, but you can't. Also, also, if you have been reading the documents and gotten familiar with Python, your first instinct might be to do like, okay, word dot replace, word is equal to word dot replace, and I'm going to replace all the i's in word. I'm going to replace all of these i's with e, with the E sound, right? And just go through and knock them all out once. But the issue is you can't do that because when you go to replace your E's with S, you're going to get for every place you put an E, because basically the replacements will start replacing the replacements and it gets too messy to deal with. So you can't just straight up use the replacement. What you have to do is that you have to go phoneme by phoneme, not letter by letter. And phonemes are one of two lengths. They're either a single letter or they're two letters in this language. Okay. A phoneme is essentially a sound. So, ka, ge, e, those are phonemes, individual sounds. And a phoneme is either going to be a single sound, be it or sorry, it's going to be either composed of a consonant. So it's going to basically be composed of consonant and then a vowel sound. So how do we do that? Well, we basically have to iterate through this. But again, we can't iterate one at a time because of those double vowels, right? So instead, what we want to use is a while loop. That's the easiest way to do this. You can use other for loops, but then you'll have to manually adjust the indexes and it gets messy. So what you'll want to do is set your index equal to 0 and say, well, index is less than the length of the word. And what you're going to want to do is you'll want to manually move through this. Let me put a pass here so that it still works. Now, where do dictionaries come in? Because this is a dictionary assignment. The dictionaries come in for translating our phonemes into vowels. We're going to use consonants. Did I spell it wrong? I bet you I did. Consonants is equal to, and that's going to be the valid consonants in here. H, W, whatever the list is. I'm not going to put them all down. That'd be a waste of our time. Well, the thing is that consonants sound exactly like the consonants. A T sounds like T, an H sounds like K, so we don't need to translate it. But on the other hand, anything involving vowels needs to be translated. For instance, we have our A's, which go to ah, our E's, which go to eh, and so on and so forth, right? I believe the E's go to eh, right? Okay. I believe like it works the same way. The vowel sounds work the same way as Japanese does, Romanji, I should say rather. So and then what we're going to do is that we're going to have a second dictionary for double vowels, because it will make it easier to check if something is there. So a double vowel, which is something like AI becomes I, right? And again, I'm not going to put them all in. They're in the document. You can put them all in yourself, right? Again, it'd be a waste of my time, but this is kind of how it gets started, right? You'll just have to manually put those in. Okay. So these will basically exist as globals for you to use in pronounce, or you can put them in pronounce if you want to. Doesn't really matter. I've just always seen them outside of that. So what we're going to do is that we're going to basically, we're going to go through index by index, and we're either going to see if we need to read two letters. So we're going to make our choice. We're either going to read two letters or one letter, and we're going to try to read two letters at once. And the reason for this is that if we read two letters, we're going to move forward two letters. If we read one letter, we're going to move forward the index forward one letter. Now, the reason we're going to check the two first is if we check the one first, we'll get we're never going to get a double vowel, because everything's going to go to, you're always going to get the single vowel and move forward one. So you got to be greedy and look for the double vowel. So how do we check to see if there's something that's a double vowel? Well, and the answer is basically we need to see if, what you need to see is that if so you're at current index, and what you want to, so say we're working with K key over here, right? And we are currently at index 1 in K key, okay? In order to get this correct, what you need to do is check, is E and I a valid double vowel character? That's kind of the first thing you check. So if we iterate through kind of the idea of the algorithm that you're going to be writing, and which I leave to you to write and figure out, the first, over here, you're going to check, okay, is KE a double vowel? How do I check if it's a double vowel? You check if it is in double vowel using the in keyword. That will check if it's one of the keys, right? If it's one of the keys, we can then translate it. But KE isn't a double vowel, okay? Is it in the vowel? No, so we don't need to translate it. Okay, so it's got to be a consonant. So we'll put that consonant down. Now, when dealing with consonants, there's a specific exception to be handled with W's. I say that you should figure that out and save that for last. It's not too bad to do, because what you're doing in that case is when you hit a W, you look to the left and see if it's making you change what that is. But that's like an edge case that can be handled last. It's like, but in general, what you do is you first check to see if the letter you're at and the next letter make a double that. Okay, so check if letter at index and next letter is a double vowel. Then otherwise check it, or rather, I'm not going to say check because I'm not telling you what to do there. If letter at index and next letter is a double vowel, handle. If letter at index is a vowel, handle that. If letter is consonant or apostrophe, handle that. And that's essentially what the bulk of the work is there. Okay, which is that, but here's the idea here is that rather than using the for loop to automatically iterate over something, you're going to be using the while loop to manually iterate over it. So you'll have to increment index by however many characters you're reading. In this first case, there'll be 2. In the second case and the third case, it'll be 1 because you're reading a single character. The other thing that will happen is that once you get this working, you'll notice that your last character will probably be ending with the last character in your. So let's assume that you get it working and you test K key. You're most likely going to end up with this K key ending with a dash. In fact, this is good. This is what you'll probably be ending up with. You'll probably end up with a hanging dash because of fence posting problems where we have, we want a dash in between everything, but the way we've programmed it is that the dash comes after every phony. The easiest way to do that is just simply remove the last character. And voila, you're done with that. Okay. Actually, in fact, I think it will be better with taking that into account. If apostrophe, apostrophe probably needs to be handled its own thing because it doesn't need a dash. But this is essentially how that program works. Okay, and again, don't worry about getting the user input, asking them for word. You can save that for the last. If you're working on that, you're essentially avoiding working on the harder part. And the parts that actually need to be done, which is the validation, which is just simply checking that everything is a valid character, and the pronunciation, which is actually doing a problem. But this probably really helps you get to the answer. And if it doesn't, think about it some more. So let me go ahead and I will copy, and I'm going to go ahead and just drop this in the Discord channel. Okay. So let me go into our class. I'm going to go to 1051 in the Discord channel. Hit tick, tick, tick. And there, I posted it in the Discord channel. You'll be able to find it in the 1051 Discord channel. Okay. But I didn't want to spend more than 20 minutes on that since for loops, you could do it with a for loop, but honestly, it's a pain because you're going to be moving because you're only for loops necessitate that you're going to be moving forward like one character at a time. So I thought you could do it. Yes, I completely blanked on that last Tuesday. So use a while loop instead. All right. So for today's exercise. Like I said, when I got in here, I'm very excited about it. It's one that I've been waiting on for a while. Hopefully you read you watched the videos the 3 videos that I put up there on Monte Carlo approximations and the Monty Hall problem. They're on the module thing for this week's stuff. So if you didn't see them here, go to Canvas, log in, because I know it's been a busy semester for everybody. It's been a busy semester for me, right? Okay, so And I mentioned at the last class, but it's totally easy to miss that I said to do that. Okay, so under modules, click on module 9, which is Monte Carlo approximation and cheating at statistics. Okay, rather than recording any lecture videos for this module, I didn't, and I just simply found lecture module of 3 videos that show this. The first is tangentially related to our Monte Carlo approximations, which is the Monty Hall problem. Okay, which is that if you have the trouble understanding what we were talking about today, or what I'm about to talk about, because I'm about to go over that Monty Hall problem, then refer back to this video. It's a great resource on it. The second is showing basically a mathematical way of doing a Monte Carlo, using Monte Carlo approximations to do something very abstract, which is computing area, I believe. And in this video over here, as I mentioned at the end of it, this is basically checking different carnival games and seeing what the chances of winning those carnival games are by doing a Monte Carlo approximation or Monte Carlo calculation, which is just somebody sat and looked at all and watched the game and and basically checked how many games were played, as well as counting how many people won the game. So like saying, okay, the game was played 500 times, but only 40 people won, because the game's rigged, Yeah, and this goes into also, and if you're interested, this goes into details about how the games are rigged. For instance, with the basketball shooting games, where normally you would be landing those 3-pointers or 2-pointers, right? It turns out that the height of the basketball is just a tad bit higher than what standard regulation NBA is, and also can be smaller too, because that's going to pop it off. Okay. So there's stuff like that, as well as this being, essentially with the way it's constructed on that, with where the arrow is pointing, that makes it more of a tightrope than that makes it very easy to spin around. It's less than being a ladder. It's a very interesting video. You should watch it. Guy does a lot of great YouTube videos. Okay. But for this one, we will go down to project 12 in Runestone, which is over here. So go to Runestone and go and open Monte Carlo simulation. I'm going to drop it in both the chat, and I will drop a link both in the chat and the Discord channel. So chat over here for all of you on Zoom. If you're not on either of those, then you can just, find it fairly straight in a fairly easy manner by, just going to your Runestone, logging in. So there's a couple ways to do this. I figure I'll start out with something exciting rather than starting out with something boring, like approximating pi, like we did back in the very beginning of the semester. Although we will be approximating it by drawing turtles. So that can be fun. But honestly, there's really nothing more exciting, in my opinion, than the Monty Hall challenge. Right. Okay. Doesn't matter. That video has been terminated. We don't need it. Okay. So the Monty Hall challenge. So there used to be a game called Let's Make a Deal. And the Monty Hall challenge the Monty Hall problem is based off of that. So you had a guy, Monty, and he was the host, Monty Hall. Let's make a deal. And what he would do is that he'd have 3 doors behind him, and you have a contestant. And I'd say, and behind those, and he'd say, behind these doors, behind one of these doors is a car, and behind the other 2 doors is a goat. Right? Now, I also should mention that the assumption is that you want the car and not the goat, because otherwise my wife would have very different targets. She likes goats, so who doesn't? Okay, but anyway, the idea here is that you want the car more than the goats. So behind one of the doors is a car, and behind the other 2 doors is a goat. And Monty says to the contestant, okay, pick door 1, 2, or 3. And the contestant picks door number 1. Now, this part is the most important part, because this is what the probabilities are depend on. Okay. Now, the contestant picks a door. Let's say he picks 1. It honestly does not matter which door he picks. Okay. The contestant picks one door, and Monty Hall opens up one of the doors and reveals a goat. He's always going to reveal goat because Monty Hall knows where the car is. So he's just going to open up one of the other doors and reveal goat. And then he's going to, and so now one of the doors has been opened, and he says, okay, you chose door number 1 or whatever you chose. Do you want to switch? And that is the Monty Hall question. Do you switch or do you stay? And this is what makes the problem so interesting, because it is unintuitive as all, which is that not only should you switch, but if you switch, you don't have a 50-50 shot of winning, which is your instinctive thoughts. If you switch, your chances of winning goes up to 66%, 2 out of 3. It's always in your interest to switch. And what makes it so unintuitive is, and if you feel like that's wrong and unintuitive, you are not alone. It became famous from reader Craig Whitaker's letter quoted to Marilyn Vosavant's Ask Marilyn in Parade magazine, where basically she was, I think it was basically ask the genius your question, right? Vosavant's response was that the contestant should switch to the other door. Upon the standard assumption, switching has a two-thirds probability of winning the car. And again, the assumption is that Monty's going to open the door and he's always going to reveal a goat. He's not going to open the door and reveal the car. Okay. And if you stay, you're, 2/3 winning, then the other chance would be only a 1/3 winning. All right. So what was interesting is that many readers of Vosavant's column refused to believe that switching was beneficial and rejected her explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, although I don't know how many of those had mathematical PhDs, wrote to the magazine, most of them calling Vosavant wrong. Even when given explanations, simulations, and formal mathematical proofs, many people did not accept that switching was the best strategy. Paul Erdos, one of the most prolific mathematicians in history, he's so prolific that many mathematicians and computer science authors have something called an Erdos number, which is essentially the math publication version of the Bacon number, right? 6 degrees of separation from Kevin Bacon. Well, the Erdos number is the mathematical version of that. That is how prolific he wrote. Anyway, he was unconvinced until he was shown a computer simulation, namely a Monte Carlo simulation. Okay. So it is, now, this had been also a solved problem before, her column. And I think it just simply, it being in the column made it what's such a high reach. And you can read more details into it because that's fascinating, as to why. But here's the explanation as to why that is the case. Okay. Right. So let's see here. So, suppose we do this, we play 300 games. On average, 100 times it's going to be behind door 3, door 1, or door 2. Let's say your strategy is always picking door number 1. Again, the door you pick doesn't actually matter initially, in the sense that, like, it doesn't matter if this would be the same if our strategy was always pick door number 2 or the strategy was pick door number 3. It doesn't matter. Okay, it's just got to be an always pick this door. So let's suppose that the car is hidden behind door 3. Okay. I picked door number 1. That means door number 1 and door number 2 have ghosts behind them. So I picked door number 1. Door 2 is revealed. If I switch, I'll get the car. Suppose the car is behind door number 1 this time, and the goats are behind here, right? So Monty opens either door 2 or door 3. Switching is going to lose in either case, right? Because I initially picked the correct car. Now suppose that it's behind door number 2. In this case, Switching also wins because he'll reveal door number 3. Remember, he always reveals the goat. If you pick the goat, he's always going to reveal the other goat. And so in this case, switching wins. So in 2 cases, switching wins. In 1 case, switching loses. Still feels unintuitive, I'm sure. Right? Here's a flow chart. The car location has a 1/3 chance of this. And again, we're assuming here that we're always picking door 1 for simplicity. Okay? Door 1, door 2, door 3. If the car is behind door 1, right? If our strategy is switching, then if we pick car 1 initially, then no matter what he reveals, we're going to get a goat. But if the car is behind either door 2 or 3, we're going to switch to that car and win. Okay. Now this is based on the fact, and what makes this work is the fact that he's always revealing where the car is. Let me go ahead and, sorry, he's always revealing where a goat is. Let me kind of demonstrate this ad absurdum. Okay. Now instead of having 3 doors, let's have 1,000,001 doors. Sorry, no, let's have 1,000,000 doors. That makes it easier. So suppose we have 1,000,000 doors. There's 999,999 goats, and there's 1 car. Not sure how we're dealing with all the goats. I'm sure they're making a huge mess of things. But regardless, we have that many doors, and we have 999,999 goats in 1 car. Okay, we pick our initial door as usual. Then Monty Hall opens up 999,998 doors, revealing 999,998 goats. You're left with 2 doors, the one you initially picked and one that you didn't. Where do you think the chances are that the car is going to be? Because that depends on whether you think your initial guess was right or not. Your initial guess was a 1 in a million shot. But it's no longer now not even a 50-50 shot because what switching is that you're betting that your initial answer was right. And your initial answer was 1 in a million. Switching is a 999,999. That's what I mean by ad absurdum. And it's the same kind of thing. We've just lowered the number of doors to 3, which is the lowest it can go. Okay, that is the problem. So that is the Monty Hall problem. It's a very well-known problem. To be honest, I was super confused until I saw a computer simulation. But the easiest way to kind of show this, right? I mean, yes, we can have the mathematics using Bayes' theorem to directly calculate it, which is H3, let's see, host opens door 3 given the cars behind door 1 and we chose car 1, right? What is the probability of that? And just multiplying those together. But that's statistics, and that uses big letters that you have to translate, and that's rough. I don't like that. But instead we can simulate this game. Yes. Yes, Monty's all. Yes, he's reducing the space, basically, of possibilities. He's always opening a goat. That's the important thing. It's always a goat that he's going to show. And again, we assume that that the case here is not this, that you don't want the goat. But I know a lot of you would be right, in which case you should stay with your initial guess. Because in that case, a guess, staying with your initial guess is you got a 2/3 shot of getting a car in that case. So, all right, but how do we prove this or show this? What we can do is we're going to do a Monte Carlo approximation of this. So what we're going to do is that we're going to write. So doing a Monte Carlo approximation is actually fairly straightforward, and it's going to always follow this format. We write a piece of code that always does a single round of whatever quote unquote game we are playing. And then and that game tells us, and then we're going to report back the result. It might be a score, or it might be, but in most cases, it's just win or lose. Now, why is this called a Monte Carlo approximation, you might ask? Okay. So for those of you who aren't too familiar, Monte Carlo is a place. It is, let's go to maps. Monte Carlo is in Europe. It's in Monaco, one of those many microstates in Europe. Europe is just dotted with microstates. Here it is. That's where it is. So this is where it is, and I'll zoom out and you'll see where it is on the map. Nice. Okay. We zoom out and we see, okay, it's like right here between France and Italy. You know, and again, France has like tons of microstates around it. Not only does it have, I mean, you might be thinking Luxembourg, but no, I'm thinking Andorra. Yeah, not the Andorra shopping center. I'm thinking like Andorra, like the country where it's ruled by co-princes, one of which is, I believe, the current president of France. So it's a very interesting form of government. Very nice. And from what I understand, very nice. But what Monaco is known for, and specifically Monte Carlo, it's known for its casino. And the idea kind of goes is that if we're going to a casino and we don't know the odds of winning a game, the easiest odds for figuring out a game, the easiest way to figure out the games at a casino without like directly trying to calculate the odds, because also, you know, if it's dealing with cards, you never know if like the dealer's like, you know, cheating with the cards or something. I mean, they shouldn't, but point being is that to figure out what your chances of winning, just like watch other players and kind of keep tally of how often people win. That's what it comes down to. So what we're going to do, so going back to this, to do this Monte Carlo approximation again, the first thing we're going to do is we're going to do a game. We're going to simulate a game. And I think what we'll do is I'll pass in a variable called strategy. Okay, so that way we can simulate the strategy of whether we stay or whether we swap, right? Right. That makes it so we can test both ways. And strategy is either, so we're either going to do what should I call it? We'll either do stay or swap. That'll be, so we're going to take in a string, okay? And that will be our choice, okay? So first thing we need to do is that we need to initialize our game, okay? And also what our strategy is for statistical simplicity is that we're always going to choose the initial door of 1, okay? We could make that a separate variable if we needed to, but honestly, it's easy if we just always choose 1 as our door. It doesn't matter which one we choose. Well, technically, since we're doing, we're working with indexes, it would be index 0, but whatever. So what we're going to do here is we're going to generate our initial, our doors. Okay, so we're going to do that as a list. And there's 3 possibilities, right? There's a goat, another goat, and a car. And I'll just use G, G, and C, right? Because there's only 2 possibilities. It makes it easy. We could write those out if we wanted to, but whatever. Now the other thing I'm going to do is, again, when we do a game, we want this to be random, right? So what we're going to do is we're going to shuffle it, right? That is the way we randomize, that we can randomize stuff. And that is part of the import module. Sorry, part of the random module, which we'll need to import. So what we'll do is we'll say random, I believe it's random.shuffle doors, and we'll test it to make sure that I'm not going, that I haven't done this completely incorrectly. I believe this shuffles it in place. So I will go down here and I will just simply print the result of our game. Sorry, I'm not even going to need to print it because when we're testing, we like to print game. And I'm just going to put foo in here right now because it's not bothering. So here, if you can see on the bottom of my screen, it does after doing the random not shuffle, it does randomize the location of my car. Of the car, I should say, right? So again, shuffle is super useful for when we have a number of things and we want to just kind of figure out and we need to swap the order. So like if we're working with the deck of cards, obviously, but also in this kind of case where we're shuffling, setting up the initial configuration of this puzzle. So now that we've got this, we've shuffled it, okay? And then let's see. So this is going to be fairly straightforward, which is that we are going to pick the first, we're going to pick, our pick is going to be, so our pick is going to be doors 0. So we're going to pick door 0, or we're going to make this pick no matter what, right? Okay. So so there's 3 possibilities. So, or rather, the possibilities are the cars behind. I initially picked the car, or I initially didn't pick the car, right? And if I picked if I picked door 0 as my initial guess, so if pick equals so if I pick that car, pick it, and I've initially picked the car, Monty's going to choose, let's say, he can choose index 1 or index 2 to reveal. It doesn't matter. It doesn't matter. Let's say he always opens up index 2, right? What our pick becomes depends on what our strategy is, right? So here, Monty reveals one of the goats. If strategy equals swap, then we're going to want to and actually I'll go into as much detail as I need to, right? If he picks one of the goats, so Monty reveals one of the goats. Reveal is equal to revealed door is equal to random dot. This is like unneeded, but I'm going to do it anyway because I wanted to be as close to reality as possible. He's going to pick either door 1 or door 2, right? If revealed door is equal to 1, what we do is he's going to reveal goat behind that door. And what we're going to do depends on our strategy, right? If our strategy is equal to swap, then our pick is equal to doors 2. Else, if our strategy was stay, our pick is going to be equal to doors 0, which we initially picked, right? Does that make sense for everybody? So first off, basically, so what we're doing here, if we initially pick the right door, because Monty would know that, right? He would know if we pick the car. He's going to randomly decide between, so if we pick door 0, he's going to, and the car's behind it, he's randomly going to pick doors 1 and 2, between 1 and 2. And then what we do next depends on our strategy. If it's door 1 and our strategy is swap, we swap to door 2. If on the other hand, he opens up 2, we're going to swap to 1. Right? Regardless if our strategy is stay, we're going to stick with door 0, right? And that's if we got it wrong initially. Else, so otherwise, if, oops. So if, what are you doing? Go home. Go home, Python. You're drunk. Okay. Elif. What are you? Oh, okay. I see what's going on there. I forgot colons. Not drunk. It's yeah, apparently. No, I'm not, but I feel like we live in a society where I have to clarify that. All right, so let's go ahead and do this. If pick is equal to, so if we picked a G, a goat initially, if door, so then Monty's going to look at the other doors and figure out which one's got the goat. If doors 1 equals a G, then he will reveal, then he's going to reveal that one and offer us a choice between door 0 and door 2. This strategy is equal to swap then we are going to swap to door 2. So pick is equal to doors 2, else our strategy is stay with it. So we're going to pick doors 0, right? Make sense? And then otherwise, if the car is behind door number 1, he won't reveal door number 1. Instead, he'll reveal door number 2. We're now offered a choice between 0 and 1, and we'll pick that. Okay, and don't worry, we'll share this, but I will go over this. If, and now the final thing is we will return a Boolean statement. Pick equals C. So true if we won by getting the car, false if we lost. Okay. And so again, what we're doing over here is we're shuffling the doors, we're making our initial pick. If our initial pick was on the car, then he's going to reveal one of the goats at random, and then we're going to either choose the other, door if we want to swap, or we're going to stay on the car if we want to, if our strategy is to stay. And again, we don't know that where the car is, but Monty knows. Else, if the door is, otherwise, if we pick a goat, okay. Oh, yep, the indentation got messed up. So there we go. Otherwise, we pick one of the goats, which means that one of the other goat is either is on door 1 or door 2, right? And then we will swap. If the other goat is behind door 1, we'll swap to 2. If the other goat is revealed to be behind door 2, we'll swap to the unopened door, which is door 1, and then we'll return. And then if we're staying, we're just always going to, be dealing with our initial choice. So let's go ahead and, print out and test it to see if it works. So I'm going to go ahead and run this. And it says, so I'm going to go ahead and unzoom for a second, even though that's going to make it tiny, but false, true, 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 false, true, true, false, true, false. We don't really get anything with by doing it, just hitting the button a bunch of times, right? There's not enough data points. So what we need is more data points. So let's go ahead and make those data points. So this does one game. Let's make a for loop that does lots of games. What's lots of games? So I'm going to make it all cap. I'm going to put trials in all caps. That means that it's kind of basically act as a constant. It's a reminder to myself that once I set it, I shouldn't touch it. Let's do 100,000 games. It's not that hard to do. And then we're going to basically say, And then what we're going to keep track of is the number of times we won the game. So we're going to simulate these games and we're going to count how many times we win. We don't need to count how many games we played because we're telling the game how many times we played. So, yep, wins is equal to 0. And now 4 in range. I don't need to type that because I put it in trials. So if I want to change the number I have, I can put it there. I'll say outcome is equal to so the outcome will be true or false. Okay. From game, and then let's put in game, and our strategy was swap. If outcome equals true, meaning we won, wins plus equals 1. And then what we do to show our win rate is very simple. We just simply take the number of wins, divide by the number of trials, and that's it. Statistics done without actually doing any statistics. We hit the run button, the save and run button, and it comes out pretty close to the results I said they would be, which is 0.668. So close to 2/3. Yep, 1051. CIS 1051. To what? Fishing. Probably not. I am very confused. I'm not going to dignify this with a response. So anyway, we've got a we've seen with the strategy of staying, we've got a 66% chance of winning. If on the other hand, we decide to basically change our strategy to stay, and we run it, and basically this means we stay with what our initial guess is, we have a 1/3 chance of winning. So again, we haven't mathematically proven, right? People on the math department would go, I have no, this is not a proof. But honestly, for pretty much everybody who's not caring about formal mathematical proofs, this is pretty good. The 33%, using this to show what's going on. Monte Carlo approximations are pretty good at this. And when we do talk about, so over the next couple of weeks, what I will be doing is I will be showing you various games of chance where the presentation of the game looks like it's fair, but in actuality, it's rigged. It's rigged against the player. Yes. Oh. I mean, I'll be sharing it. So again, but this is essentially what the main loop of any Monte Carlo approximation is going to be. Yes. Swap, meaning our strategy is going to be swapping. In other words, we have our initial choice, and then what our secondary choice is going to be. Can you please mute that? So the swap strategy means that we are going to be, that given our initial choice, we are going to swap to another door. And if our strategy is stay, that means we're going to stay with our initial choice. So in other words, during swap, Monty's always going to show, is always going to reveal one of the doors and say, do you want to swap to your, to this, do you want to stay with your choice, or do you want to swap to this door that you don't know what's behind? It's just the name of the strategy. All right. Yes. Oh, sorry. I thought that was your hand up. Generally 100,000 a trial. I mean, it depends on how many significant figures you want, right? Running 10 trials is only going to give you one significant figure. Running 100 is going to give you two. Running 1,000 is going to give you three significant figures. Yep. So, but in general, it just depends on how strong your argument needs to be, or how precise your measurements need to be. All right. All right, so now we're going to move on to something a bit more abstract, yet going to be interesting, which is approximating pi. All right, have a nice day. I assume I have just been a victim of some kind of performance art. All right. Have a great day. All right. So earlier in the semester, we did a very boring Monte Carlo we did a very boring method of calculating the value of pi by, if you remember this Leibniz formula, calculating pi over 4 by adding successively smaller fractions to each other, adding and subtracting. But instead, there's a different way to do this, which is throwing darts on a dartboard. That's one, and that is the Monte Carlo approximation of you know, approximating pi. It turns it into kind of a game. The idea here is that we're going to have some kind of dartboard, okay? And yes. Oh, yes, of course. No worries. It was mildly distracted. All right. So the idea here for how does this throwing darts on a dartboard approach work for figuring out the value of pi, because that sounds like a bunch of nonsense. The idea here, I grabbed my pen, I'm sure. Mute whiteboard. Okay, so suppose we have a circle. Assume that's a circle because I can't draw that well. All right. So we're going to put this, so this circle is going to be centered right here, and that point is going to be 0, 0. Okay. So this point is 0, 0, and the circle is going to have a radius of 1. So your standard unit circle, okay, has a radius of 1. I'm going to draw, and now I'm going to draw a box around it, squaring the circle, which if you aren't familiar, that's like one of those nasty things you give as a task to a person. Tell them to draw a circle around a circle and a square. So the idea here is that we've got this unit 1, this circle with a radius of 1. So how big is the square? Like how big is the side of the square? Well, so the radius is 1, right? So this square has a side of 2. All right. And the idea here is that, let's see, I want to make sure I say this right. So the idea here is that this is our dartboard, and we're going to assume that all the darts land in this dartboard. Okay, the circle being the target, and then the area outside the circle being not a hit. Okay, and yes, there's a magical force field that ensures that everything is in there. All right. So all of our darts are either going to land inside that circle or they're going to land outside the circle. All right. So we know this because, okay, so what is the area of, so we can figure out both the area of the circle and the area of the square, right? The area of this square, since you know, it's got a side of 2, it's the square, you know, it's just simply 2 squared, which would be 4. So area of the square, our big area, is 4. And the area of the circle is 2 pi. Right? What is it? 2 pi r. 2 pi. So the area of a circle is pi r squared. Right? Area of a circle is pi r squared. What's r in this case? R is 1, meaning that 1 squared is 1, meaning that the area of the circle is pi. So very simply put, the ratio of things that land inside the circle versus, so if we calculate the stuff that lands inside the circle versus the stuff that all the darts we throw, that's going to be pi over 4, right? Because if we throw some number of dice, some number of darts, pi proportion of them are going to land in this area, and the rest are going to land in here. Basically, out of 4, which is the possible area we could hit, pi of it is taken up by the circle, meaning that if we just simply hit it with a bunch of these darts, that's how many are going to be that's the proportion of the area. This is a proportion. I know it's a bit weird. So, but the idea here is that we are simply comparing the radius of the circle to the radius of the area of the circle to the area of the square. Which means that, again, we're just going to count the amount of things that land in this. How do we calculate? So how do we throw a dart? We throw a dart by generating a random number between between -1 and 1. Because again, we're centered at 0, 0. Right? Makes sense? Centered at 0, 0. All right. So first thing we're gonna do this with turtles, because what's the point of doing this mathematically unless we draw it? So what we're gonna do is we're gonna use something that was used in the background of your hurricane tracker, which is the set world coordinates. And what set world coordinates does, okay, is that it changes the plane that the world that the turtle is working in. So if we import turtle, okay, and we say turtle dot set, let's see, world coordinates. Okay, we basically dictate what the area of what part is being drawn. We're going to say how big his world is. So, and we specify basically the lower left of the rectangle that he's in and the upper left of the rectangle he's in. The lower left being, you know, lower left X and Y being -1, -1, right? That's where, so -1, -1 over here, and then 1, 1 over here for that. Okay, and let's go ahead and run this and make sure it works. So, and now if I do Bob is equal to turtle dot turtle, and I say Bob dot forward 1. That's normally 1 pixel. Let's see. But he didn't just move forward 1 pixel. I changed the way this works, where 1 pixel was a unit of movement. Now I'm saying, if I tell you 1, he's moving to the perimeter of this, right? So essentially, this means that this square that Bob is in is the square that I was talking about. So what I've done is I've set up the world coordinates. So, so now what we do need to do is we got to throw a dart, which is, in order to throw a dart, we have a def throw dart. And what it's going to do is to throw a dart is going to be pretty simple. I'm going to generate an X and Y coordinate, and then I'm going to move the turtle there. Okay. So I'm going to throw dart, and our turtle is going to act as a dart. My wife is a zoologist. Please do not tell her that I am throwing turtles around. No, she's a biologist. She works at Philadelphia Zoo. Don't think she's technically a zoologist. I don't know, but she's a biologist. So, and she likes turtles. So let's go ahead and go through this. So, sorry. Oh, we will need to. So we'll go ahead and do that now. Import random. And then we're going to need to we're going to need to generate not an integer, but a float. So random float Python. I'm just, again, off the top of my head, I want to make sure I get this right. So random returns something between 0 and 1. Float range, right, it's random.uniform. Yep, random.uniform. Which will return a floating point between the numbers A and B. And the idea here is that, and the reason it's called uniform is because it's a point, is because all these points will be selected uniformly at random. Okay. So let's see. So we're going to generate the X as a random.uniform -1 to 1, Y as random.uniform okay, 1 to 1, and we'll say, and let's go ahead and say Bob dot pen up so that he's not actually going to be drawing stuff as he moves. Bob dot go to X comma Y. Bob dot stamp. And so we'll tell him to go. So we generate an X and Y, we tell Bob to go there, and he will just simply stamp there. And then we'll just simply call it throw dart Bob. So we're going to toss Bob, and he ends up there. And then if I run this again, he's going to end up somewhere else. And then if I change this to be in a for loop, and to do this a bunch of times, for in range, so let's go ahead and do trials again, is equal to 100,000. Actually, it's going to take a while, so I want to do 100. For range in trials. Again, I'm just putting this in for loop to run 100 times. Save and run, and we see that we draw stuff all over the place. Not particularly the most compelling, though. So instead, let's color it to show you whether or not we did a hit or not. Okay, we know if it's going to be a hit based on the distance formula. Simply put, it's a hit if it lands inside the circle. And how do we know if it lands inside the circle? Well, the circle has a radius 1. So if the distance from 0, 0, if the Euclidean distance from 0, 0 is greater than 1, then it's a miss. Otherwise, it's a hit. So again, for those of you who have, and for those of you who forget how to calculate Euclidean distance, we just simply take the X coordinate, square it, the Y coordinate, square it, add them together, and then take the square root. That gives us the Euclidean distance. So what we're going to do over here is that I'm going to add some extra spice here, let's say. So I'm going to say distance is d, which is distance, is equal to math dot. So I'll have to import math as well. Import math dot square root of x squared plus y squared. Nice and easy to do in Python. If d is less than, if d is less than or equal to 1, then that's a hit. We'll say Bob dot color. I think that's how you change his color. Bob dot color is blue. We'll tell him to go to X, Y. What? Is that color? Oh, we'll see. And then else. No, it's possible you're right. There's pen color, and then I think there's other colors as well. And then otherwise we'll go in red. And the reason I'm doing this is because I need him to go to X, Y. I need him to stamp. And then I'm going to return true for a hit. And then return false for a miss. Because we'll be using those true and falses to calculate our data. And again, I will share this. And now we can see that we get this. We need to change the way this works though, because we need a lot more calculations for this to work. Turtle tracer. Okay. So that's not what I want. I want the Control F tracer, animation control, turtle tracer. So setting it to N delay. So what do you suggest? Skips update and then only wait. So, okay. So this will help basically, and what this will do is that we'll basically pause and just try to do a bunch of animation all at once. So turtle dot tracer 100 10, and this will take some experimenting to see how it draws, but we want it to draw nice and right for us. Oops. Why did it say pen? Oh, okay. Why did it say? So I don't want, why did it say pen? So I did Bob dot pen up. Maybe it needs to be Bob. Yes. And now it goes much, much faster. So as a result, we can increase the number of trials to maybe 10,000. So we've thrown enough darts and we can tell, hey, we hit, this is, the blue's where we hit and the red's where we didn't. And it looks a bit grainy because of the number of results we get, but also because of the shape of the turtle. It's yeah. To do what? Tracer. Bob the tracer 110. All right. So now again, what we're going to try to do is we will now calculate pi over 4 by counting the number of hits. Hits is equal to 0. Throw dart. So if throw dart, if we return true on a hit, if throw dart is equal to, if that's true, then hits plus equals 1. And that's all we need to do there. So now what we can do is we can print hits divided by trials, which should approximate pi over 4. But because we are way more familiar with pi, I'm going to go ahead and multiply this by 4 so that it will, instead of approximating pi, this is going to, pi over 4 is going to approximate pi. And so I'll run this and it's going to draw. And we'll see that it says is that I've got 3.17. Not a good approximation. It's not a good approximation with only, in fact, it's a very slow approximation. What it is useful for is this is actually a useful test for testing distributed computation, because you can give it to a bunch of independent processors who can all collate their answer without having to coordinate with each other significantly. They can all perform this task kind of independently. Let's go ahead and see if I do 1,000. Oh yeah, that generated really quickly. If I just kind of change that to 1,000, kind of generated instantly. Okay. So now let me go up to 100,000 trials. And we'll see with 100,000 trials that we get 3.14. So that's about, so we're at a third grader approximation. That's nice. Sorry? Yep, hits divided by trials, but I multiplied it all by 4 because the trials over, hits over trials will, we'd be expecting pi, which is the area of the circle, over 4, which is the radius, which is the total area of the square. But we want to see pi, but we don't have pi over 4 memorized. What I do have memorized is pi. So I'm multiplying by 4 to get rid of the pi, that over 4 part, so that we can see that it's approximating pi. So Monte Carlo approximations like this are extremely fun. If you want, now for those of you who are interested so one possible, so this can be used in a lot of ways. For those of you who are very kind of into like finance and stuff, one interesting idea for a final project might be stock prediction. After all, past performance is the best indicator of future performance, so they say. So the idea here is that here's a bunch of Apple stock from 2006 and 2007 and 2008, all the way actually, so all the daily averages from 2006 to 2010. And so the idea here is using Monte Carlo approximations to predict the next, the next 200 days or so of performance. I should point out that, like, that a lot of times, experts will predict how stocks and stuff will perform, and they perform as well as a cat randomly picking the stocks. So take that as you may. But it's still a useful kind of simulation. And if you're wondering how to make money on the stock market, the answer is index funds. There you go. All right. So with that, we will talk about more games that might be used to scam you at a bar. And then we will look at things that are, and then we'll also look at the pig game and how that is a Monte Carlo.
So for the Hawaii